Lightning.
Lightning is a massive electrostatic discharge between the electrically charged regions within clouds or between a cloud and the surface of a planet. The charged regions within the atmosphere temporarily equalize themselves through a lightning flash, commonly referred to as a strike if it hits an object on the ground. There are three primary types of lightning. From a cloud to itself. From one cloud to another cloud and between a cloud and the ground. Although lightning is always accompanied by the sound of thunder, distant lightning may be seen but be too far away for the thunder to be heard.
General considerations.
On Earth, the lightning frequency is approximately 40 to 50 times a second or nearly 1.4 billion flashes per year. Many factors affect the frequency, distribution, strength and physical properties of a typical lightning flash in a particular region of the world. These factors include ground elevation, latitude, prevailing wind currents, relative humidity, proximity to warm and cold bodies of water, etc. To a certain degree, the ratio between IC, CC and CG lightning may also vary by season and middle latitudes. Because human beings are terrestrial and most of their possessions are on the Earth, where lightning can damage or destroy them, CG lightning is the most studied and best understood of the three types, even though IC and CC are more common types of lightning. Lightning's relative unpredictability limits a complete explanation of how or why it occurs, even after hundreds of years of scientific investigation. A typical cloud-to-ground lightning flash culminates in the formation of an electrically conducting plasma channel through the air in excess of 5 kilometers, 3.1 miles, tall, from within the cloud to the ground's surface. The actual discharge is the final stage of a very complex process. At its peak, a typical thunderstorm produces 3 or more strikes to the Earth per minute. Lightning primarily occurs when warm air is mixed with colder air masses, resulting in atmospheric disturbances necessary for polarizing the atmosphere. However, it can also occur during dust storms, forest fires, tornadoes, volcanic eruptions, and even in the cold of winter, where the lightning is known as thundersnow. Hurricanes typically generate some lightning, mainly in the rain bands as much as 160 kilometers, 99 miles, from the center. The science of lightning is called fulminology, and the fear of lightning is called astrophobia.
General properties.
Lightning is not distributed evenly around the planet, as seen in the image on the right. About 70% of lightning occurs over land in the tropics where atmospheric convection is the greatest. This occurs from both the mixture of warmer and colder air masses, as well as differences in moisture concentrations, and it generally happens at the boundaries between them. The flow of warm ocean currents past drier land masses, such as the Gulf Stream, partially explains the elevated frequency of lightning in the southeast United States. Because the influence of small or absent land masses in the vast stretches of the world's oceans limits the differences between these variants in the atmosphere, lightning is notably less frequent there than over larger landforms. The North and South Poles are limited in their coverage of thunderstorms and therefore result in areas with the least amount of lightning. In general, cloud-to-ground, CG, lightning flashes account for only 25% of all total lightning flashes worldwide. Since the base of a thunderstorm is usually negatively charged, this is where most CG lightning originates. This region is typically at the elevation where freezing occurs within the cloud. Freezing, combined with collisions between ice and water, appears to be a critical part of the initial charge development and separation process. During wind-driven collisions, ice crystals tend to develop a positive charge, while a heavier, slushy mixture of ice and water, called graupel, develops a negative charge. Updrafts within a storm cloud separate the lighter ice crystals from the heavier graupel, causing the top region of the cloud to accumulate a positive space charge while the lower level accumulates a negative space charge. Because the concentrated charge within the cloud must exceed the insulating properties of air, and this increases proportionally to the distance between the cloud and the ground, the proportion of CG strikes, versus cloud-to-cloud, CC, or in cloud, IC, discharges, becomes greater when the cloud is closer to the ground. In the tropics, where the freezing level is generally higher in the atmosphere, only 10% of lightning flashes are CG. At the latitude of Norway, around 60° north latitude, where the freezing elevation is lower, 50% of lightning is CG. Lightning is usually produced by cumulonimbus clouds, which have bases that are typically 1 to 2 kilometers, 0.6 to 1.25 miles, above the ground and tops up to 15 kilometers, 9.3 miles, in height. On Earth, the place where lightning occurs most often is near the small village of Kafuka in the mountains of the Eastern Democratic Republic of the Congo, where the elevation is around 975 m, 3,200 feet. On average, this region receives 158 lightning strikes per 1 square kilometer, 0.39 square miles, per year. Other lightning hotspots include Catatumbo lightning in Venezuela, Singapore, Teresina in northern Brazil, and Lightning Alley in central Florida.
Establishing conditions necessary for lightning.
In order for an electrostatic discharge to occur, two things are necessary: 1, a sufficiently high electric potential between two regions of space must exist. And 2, a high-resistance medium must obstruct the free, unimpeded equalization of the opposite charges. It is well understood that during a thunderstorm there is charge separation and aggregation in certain regions of the cloud. However, the exact processes by which this occurs are not fully understood. Main article, Thunderstorm. The atmosphere provides the electrical insulation, or barrier, that prevents free equalization between charged regions of opposite polarity. This is overcome by lightning, a complex process referred to as the lightning flash, establishing the electric field in CG lightning.
Lightning flashes and strikes.
The best studied and understood form of lightning is crowd-to-ground, CG. Although more common, intra-cloud, IC, and cloud-to-cloud, CC, flashes are very difficult to study given there are no physical points to monitor inside the clouds. Also, given the very low probability lightning will strike the same point repeatedly and consistently, scientific inquiry is difficult at best even in the areas of high CG frequency. As such, knowing flash propagation is similar amongst all forms of lightning. The best means to describe the process is through an examination of the most studied form, cloud-to-ground.
Downward leader formation for negative CG lightning.
In a process not well understood, a channel of ionized air, called a leader, is initiated from a negatively charged region in the thundercloud. Leaders are electrically conductive channels of partially ionized gas that travel away from a region of dense charge. Negative leaders propagate away from densely charged region of negative charge, and positive leaders propagate from positively charged regions. The positively and negatively charged leaders proceed in opposite directions, positive upwards within the cloud and negative towards the Earth. Both ionic channels proceed, in their respective directions, in a number of successive spurts. Each leader pools ions at the leading tips, shooting out one or more new leaders, momentarily pooling again to concentrate charged ions, then shooting out another leader. Leaders often split, forming branches in a tree-like pattern. In addition, negative leaders travel in a discontinuous fashion. The resulting jerky movement of these step leader, S, can be readily observed in slow-motion videos of negative leaders as they head toward ground prior to a negative CG lightning strike. The negative leaders continue to propagate and split as they head downward, often speeding up as they get closer to the Earth's surface. About 90% of ionic channel lengths between pools are approximately 45 m, 148 feet, in length. The establishment of the ionic channel takes a comparatively long amount of time, hundreds of milliseconds, in comparison to resulting discharge which occurs within a few microseconds. The electric current needed to establish the channel, measured in the tens or hundreds of amperes, is dwarfed by subsequent currents during the actual discharge. Initiation of the outward leaders is not well understood. The electric field strength within the thundercloud is not typically large enough to initiate this process by itself. Many hypotheses have been proposed. One theory postulates that showers of relativistic electrons are created by cosmic rays and are then accelerated to higher velocities via a process called runaway breakdown. As these relativistic electrons collide and ionize neutral air molecules, they initiate leader formation. Another theory invokes locally enhanced electric fields being formed near elongated water droplets or ice crystals. Percolation theory, especially for the case of biased percolation, describes random connectivity phenomena, which produce an evolution of connected structures similar to that of lightning strikes.
Upward streamers.
When a stepped leader approaches the ground, the presence of opposite charges on the ground enhances the strength of the electric field. The electric field is strongest on grounded objects whose tops are closest to the base of the thundercloud, such as trees and tall buildings. If the electric field is strong enough, a positively charged ionic channel, called a positive or upward streamer, can develop from these points. This was first theorized by Heinz Casimir. As negatively charged leaders approach, increasing the localized electric field strength, grounded objects already experiencing corona discharge exceed a threshold and form upward streamers.
Attachment.
Once a downward leader connects to an available upward leader, a process referred to as attachment, a low-resistance path is formed and discharge may occur. Photographs have been taken on which unattached streamers are clearly visible. The unattached downward leaders are also visible in branched lightning, none of which are connected to the Earth, although it may appear they are.
Discharge.
Return stroke. Once a conductive channel bridges the ionized air between the negative charges in the cloud and the positive surface charges below, the floodgates are opened, and a massive electrical discharge follows. Neutralization of positive surface charges occurs first. An enormous current of positive charges races up the ionic channel towards the thundercloud. This is the return stroke and it is the most luminous and noticeable part of the lightning discharge. The positive charges in the ground region surrounding the lightning strike are neutralized within microseconds as they race inward to the strike point, up the plasma channel, and back to the cloud. A huge surge of current creates large radial voltage differences along the surface of the ground. Called step potentials, they are responsible for more injuries and deaths than the strike itself. Electricity follows the path of least resistance. A portion of the return stroke current will often preferentially flow through one leg and out another, electrocuting an unlucky human or animal standing near the point where the lightning strikes. The electrical current of the return stroke averages 30 kA for a typical negative CG flash, often referred to as negative CG lightning. In some cases, a positive ground-to-cloud (GC) lightning flash may originate from a positively charged region on the ground below a storm. These discharges normally originate from the tops of very tall structures, such as communications antennas. The rate at which the return stroke current travels has been found to be around 1x108 ms. The massive flow of electrical current occurring during the return stroke combined with the rate at which it occurs, measured in microseconds, rapidly superheats the completed leader channel, forming a highly electrically conductive plasma channel. The core temperature of the plasma during the return stroke may exceed 50,000 K, causing it to brilliantly radiate with a blue-white color. Once the electrical current stops flowing, the channel cools and dissipates over tens or hundreds of milliseconds, often disappearing as fragmented patches of glowing gas. The nearly instantaneous heating during the return stroke causes the air to explosively expand, producing a powerful shock wave that is heard as thunder. Restrike. High-speed videos, examined frame by frame, show that most negative CG lightning flashes are made up of 3 or 4 individual strokes, though there may be as many as 30. Each restrike is separated by a relatively large amount of time, typically 40 to 50 milliseconds, as are the charged regions in the cloud are discharged in subsequent strokes. Restrikes often cause a noticeable strobe light effect. Each successive stroke is preceded by intermediate dart leader strokes that have a faster rise time but lower amplitude than the initial return stroke. Each subsequent stroke usually reuses the discharge channel taken by the previous one, but the channel may be offset from its previous position as wind displaces the hot channel. Transient currents during the flash. The electrical current within a typical negative CG lightning discharge rises very quickly to its peak value in 1 to 10 microseconds, then decays more slowly over 50 to 200 microseconds. The transient nature of the current within a lightning flash results in several phenomena that need to be addressed and the effective protection of ground-based structures. Rapidly changing currents tend to travel on the surface of a conductor. This is called skin effect, unlike direct currents flowing through the entire conductor like water through a hose. Hence, conductors used in the protection of facilities tend to be multi-stranded small wires woven together, that increases the surface area inversely in proportion to cross-sectional area. The rapidly changing currents also create electromagnetic pulses, EMPs, that radiate outward from the ionic channel. This is a characteristic of all electrical sparks. The radiated pulses rapidly weaken as their distance from the origin increases. However, if they pass over conductive elements, that is, electrical wires, communication lines or metallic pipes, they may induce a current which travels outward to its termination. This is the surge that more often than not, results in the destruction of delicate electronics, electrical appliances or electric motors. Devices known as surge protectors, SPD, or transient voltage surge suppressors, TVSS, attached in series with these conductors can detect the lightning flash's transient current, and through an alteration of its physical properties, route the spike to an attached earthing ground, thereby protecting the equipment from damage.
Types.
There are three primary types of lightning, defined by what is at the ends of a flash channel. They are intra-cloud, IC, which occurs within a single thundercloud unit. Cloud-to-cloud, CC, which starts and ends between two different functional thundercloud units. And cloud-to-ground, that primarily originates in the thundercloud and terminates on an Earth surface, but may also occur in the reverse direction, that is ground-to-cloud. There are variations of each type, such as positive versus negative CG flashes, that have different physical characteristics common to each which can be measured. Different common names used to describe a particular lightning event may be attributed to the same or different events.
Cloud-to-ground CG.
Cloud-to-ground is the best known and third most common type of lightning. It is the best understood of all forms because it allows for scientific study given it terminates on a physical object, namely the Earth, and lends itself to being measured by instruments. Of the three primary types of lightning, it poses the greatest threat to life and property since it terminates or strikes the Earth. Cloud-to-ground, CG, lightning is a lightning discharge between a thundercloud and the ground. It is usually negative in polarity and is usually initiated by a stepped leader moving down from the cloud. Ground-to-cloud lightning is an artificially initiated, or triggered, category of CG flashes. Triggered lightning originates from tall, positively charged structures on the ground, such as towers on mountains that have been inductively charged by the negative cloud layer above. Positive and negative lightning.
Cloud-to-cloud CC and intra-cloud IC.
Lightning discharges may occur between areas of cloud without contacting the ground. When it occurs between two separate clouds it is known as inter-cloud lightning, and when it occurs between areas of differing electric potential within a single cloud it is known as intra-cloud lightning. Intra-cloud lightning is the most frequently occurring type. Intra-cloud lightning most commonly occurs between the upper anvil portion and lower reaches of a given thunderstorm. This lightning can sometimes be observed at great distances at night as so-called heat lightning. In such instances, the observer may see only a flash of light without hearing any thunder. The heat portion of the term is a folk association between locally experienced warmth and the distant lightning flashes. Another terminology used for cloud-cloud or cloud-cloud ground lightning is anvil crawler, due to the habit of the charge typically originating from beneath or within the anvil and scrambling through the upper cloud layers of a thunderstorm, normally generating multiple branch strokes which are dramatic to witness. These are usually seen as a thunderstorm passes over the observer or begins to decay. The most vivid crawler behavior occurs in well-developed thunderstorms that feature extensive rear anvil shearing.
Dark lightning.
A team of physicists, including Joseph Dwyer at Florida Tech, have developed a model of how thunderstorms produce high-energy radiation. In this model, instead of lightning, thunderstorms can also result in an electrical breakdown of high-energy electrons and the antimatter equivalent, positrons. The interaction between the electrons and positrons creates explosive growth in some of these high-energy particles, emitting the observed terrestrial gamma-ray flashes and rapidly discharging the thunder cloud, sometimes even faster than normal lightning. Even though abundant gamma rays are emitted by this process, with little or no visible light, it creates an electrical breakdown within the storms now called dark lightning by the scientific community.
Observational variations.
Ball lightning may be an atmospheric electrical phenomenon, the physical nature of which is still controversial. The term refers to reports of luminous, usually spherical objects which vary from pea-sized to several meters in diameter. It is sometimes associated with thunderstorms, but unlike lightning flashes, which last only a fraction of a second, ball lightning reportedly lasts many seconds. Ball lightning has been described by eyewitnesses but rarely recorded by meteorologists. Scientific data on natural ball lightning is scarce owing to its infrequency and unpredictability. The presumption of its existence is based on reported public sightings, and has therefore produced somewhat inconsistent findings. Bead lightning refers to the decaying stage of a lightning channel in which the luminosity of the channel breaks up into segments. Nearly every lightning discharge will exhibit beading as the channel cools immediately after a return stroke, sometimes referred to as the lightning's bead-out stage. Bead lightning is more properly a stage of a normal lightning discharge rather than a type of lightning in itself. Beading of a lightning channel is usually a small-scale feature, and therefore is often only apparent when the observer camera is close to the lightning. Dry lightning is used in Australia, Canada and the United States for lightning that occurs with no precipitation at the surface. This type of lightning is the most common natural cause of wildfires. Pyrocumulus clouds produce lightning for the same reason that it is produced by cumulonimbus clouds. Forked lightning is crowd-to-ground lightning that exhibits branching of its path. Heat lightning is a lightning flash that appears to produce no discernible thunder because it occurs too far away for the thunder to be heard. The sound waves dissipate before they reach the observer. Ribbon lightning occurs in thunderstorms with high crosswinds and multiple return strokes. The wind will blow each successive return stroke slightly to one side of the previous return stroke, causing a ribbon effect. Rocket lightning is a form of cloud discharge, generally horizontal and at cloud base, with a luminous channel appearing to advance through the air with visually resolvable speed, often intermittently. Sheet lightning refers to cloud-to-cloud lightning that exhibits a diffuse brightening of the surface of a cloud, caused by the actual discharge path being hidden or too far away. The lightning itself cannot be seen by the spectator, so it appears as only a flash, or a sheet of light. The lightning may be too far away to discern individual flashes. Staccato lightning is a cloud-to-ground lightning, (CG) strike which is a short-duration stroke that, often but not always, appears as a single very bright flash and often has considerable branching. These are often found in the visual vault area near the mesocyclone of rotating thunderstorms and coincides with intensification of thunderstorm updrafts. A similar cloud-to-cloud strike consisting of a brief flash over a small area, appearing like a blip, also occurs in a similar area of rotating updrafts. Superbolts are bolts of lightning around 100 times brighter than normal. On Earth, 1 in a million lightning strikes is a superbolt. Sympathetic lightning refers to the tendency of lightning to be loosely coordinated across long distances. Discharges can appear in clusters when viewed from space. Clear air lightning is used in Australia, Canada and the United States to describe lightning that occurs with no apparent cloud close enough to have produced it. In the US and Canadian Rockies, a thunderstorm can be in an adjacent valley and not observable from the valley where the lightning bolt strikes either visually or audibly. European and Asian mountainous areas experience similar events. Also in areas such as sounds, large lakes or open plains, when the storm cell is on the near horizon, within 26 kilometers, 16 miles there may be some distant activity, a strike can occur, and as the storm is so far away, the strike is referred to as clear air.
Effects. Lightning strike.
Objects struck by lightning experience heat and magnetic forces of great magnitude. The heat created by lightning currents traveling through a tree may vaporize its sap, causing a steam explosion that bursts the trunk. As lightning travels through sandy soil, the soil surrounding the plasma channel may melt, forming tubular structures called fulgurites. Humans or animals struck by lightning may suffer severe injury or even death due to internal organ and nervous system damage. Buildings or tall structures hit by lightning may be damaged as the lightning seeks unintended paths to ground. By safely conducting a lightning strike to ground, a lightning protection system can greatly reduce the probability of severe property damage.
Thunder.
Because the electrostatic discharge of terrestrial lightning superheats the air to plasma temperatures along the length of the discharge channel in a short duration, kinetic theory dictates gaseous molecules undergo a rapid increase in pressure and thus expand outward from the lightning, creating a shock wave audible as thunder. Since the sound waves propagate not from a single point source but along the length of the lightning's path, the sound origins varying distances from the observer can generate a rolling or rumbling effect. Perception of the sonic characteristics is further complicated by factors such as the irregular and possibly branching geometry of the lightning channel, by acoustic echoing from terrain, and by the typically multiple stroke characteristic of the lightning strike. Light travels at about 300 million meters per second. Sound travels through air at about 340 meters per second. An observer can approximate the distance to the strike by timing the interval between the visible lightning and the audible thunder it generates. A lightning flash preceding its thunder by 5 seconds would be about 1 mile, 1.6 kilometers, 5x 340 m, distant. A flash preceding thunder by 3 seconds is about 1 kilometer, 0.62 miles, 3x 340 m, distant. Consequently, a lightning strike observed at a very close distance will be accompanied by a sudden clap of thunder, with almost no perceptible time lapse, possibly accompanied by the smell of ozone, O3.
High-energy radiation.
The production of X-rays by a bolt of lightning was theoretically predicted as early as 1925, but no evidence was found until 2001/2002, when researchers at the New Mexico Institute of Mining and Technology detected X-ray emissions from an induced lightning strike along a grounded wire trailed behind a rocket shot into a storm cloud. In the same year, University of Florida and Florida Tech researchers used an array of electric field and X-ray detectors at a lightning research facility in North Florida to confirm that natural lightning makes X-rays in large quantities during the propagation of steppe leaders. The cause of the X-ray emissions is still a matter for research, as the temperature of lightning is too low to account for the X-rays observed. A number of observations by space-based telescopes have revealed even higher energy gamma-ray emissions, the so-called terrestrial gamma-ray flashes, TGFs. These observations pose a challenge to current theories of lightning, especially with the recent discovery of the clear signatures of antimatter produced in lightning.
Volcanic.
Volcanic activity produces lightning-friendly conditions in multiple ways. The enormous quantity of pulverized material and gases ejected into the atmosphere with explosive power, creates a dense plume of highly charged particles, which establishes the perfect conditions for lightning. The ash density and constant motion within the volcanic plume continually produces electrostatic ionization, resulting in very powerful and very frequent flashes attempting to neutralize itself. Due to the extensive solid material, ash, content, unlike the water-rich charge-generating zones of a normal thundercloud, it is often called a dirty thunderstorm. Powerful and frequent flashes have been witnessed in the volcanic plume as far back as the 79 AD eruption of Vesuvius by Pliny the Younger. Likewise, Vapors and ash originating from vents on the volcano's flanks may produce more localized and smaller flashes upwards of 2.9 kilometers long. Small, short-duration sparks, recently documented near newly extruded magma, attest to the material being highly charged prior to even entering the atmosphere.
Extraterrestrial lightning.
Lightning has been observed within the atmospheres of other planets, such as Venus, Jupiter and Saturn. Although in the minority on Earth, superbolts appear to be common on Jupiter. Lightning on Venus has been a controversial subject after decades of study. During the Soviet Venera and U.S. Pioneer missions of the 1970s and 1980s, signals suggesting lightning may be present in the upper atmosphere were detected. Although the Cassini-Huygens mission flyby of Venus in 1999 detected no signs of lightning, the observation window lasted mere hours. Radio pulses recorded by the spacecraft Venus Express, which began orbiting Venus in April 2006, have been confirmed to originate from lightning on Venus.
Human-related.
Airplane contrails have also been observed to influence lightning to a small degree. The water vapor-dense contrails of airplanes may provide a lower resistance pathway through the atmosphere, having some influence upon the establishment of an ionic pathway for a lightning flash to follow. Rocket exhaust plumes provided a pathway for lightning when it was witnessed striking the Apollo 12 rocket shortly after takeoff. Thermonuclear explosions, by providing extra material for electrical conduction and a very turbulent localized atmosphere, have been seen triggering lightning flashes within the mushroom cloud. In addition, intense gamma radiation from large nuclear explosions may develop intensely charged regions in the surrounding air through Compton scattering. The intensely charged space charge regions create multiple clear air lightning discharges shortly after the device detonates.
Scientific study. Properties.
Thunder is heard as a rolling, gradually dissipating rumble because the sound from different portions of a long stroke arrives at slightly different times. When the local electric field exceeds the dielectric strength of damp air, about 3 million volts per meter, electrical discharge results in a strike, often followed by commensurate discharges branching from the same path. See image, right. Mechanisms that cause the charges to build up to lightning are still a matter of scientific investigation. Lightning may be caused by the circulation of warm moisture-filled air through electric fields. Ice or water particles then accumulate charges in a van der Graaf generator. Researchers at the University of Florida found that the final one-dimensional speeds of 10 flashes observed were between 1.0x105 and 1.4x106 ms, with an average of 4.4x105 ms.
Detection and monitoring.
The earliest detector invented to warn of the approach of a thunderstorm was the lightning bell. Benjamin Franklin installed one such device in his house. The detector was based on an electrostatic device called the electric chimes invented by Andrew Gordon in 1742. Lightning discharges generate a wide range of electromagnetic radiations, including radio frequency pulses. The times at which a pulse from a given lightning discharge arrives at several receivers can be used to locate the source of the discharge. The United States federal government has constructed a nationwide grid of such lightning detectors, allowing lightning discharges to be tracked in real time throughout the continental U.S. The Earth ionosphere waveguide traps electromagnetic VLF and ELF waves. Electromagnetic pulses transmitted by lightning strikes propagate within that waveguide. The waveguide is dispersive, which means that their group velocity depends on frequency. The difference of the group time delay of a lightning pulse at adjacent frequencies is proportional to the distance between transmitter and receiver. Together with direction-finding methods, this allows to locate lightning strikes up to distances of 10,000 km from their origin. Moreover, the eigenfrequencies of the Earth ionospheric waveguide, the Schumann resonances at about 7.5 Hz, are used to determine the global thunderstorm activity. In addition to ground-based lightning detection, several instruments aboard satellites have been constructed to observe lightning distribution. These include the Optical Transient Detector, OTD, aboard the OrbView 1 satellite launched on April 3, 1995, and the subsequent Lightning Imaging Sensor, LIS, aboard TRMM launched on November 28, 1997.
Artificially triggered.
Rocket-triggered lightning can be triggered by launching specially designed rockets trailing spools of wire into thunderstorms. The wire unwinds as the rocket ascends, creating an elevated ground that can attract descending leaders. If a leader attaches, the wire provides a low-resistance pathway for a lightning flash to occur. The wire is vaporized by the return current flow, creating a straight lightning plasma channel in its place. This method allows for scientific research of lightning to occur under a more controlled and predictable manner, laser-triggered.
Physical manifestations. Lightning-induced magnetism.
The movement of electrical charges produces a magnetic field, see electromagnetism. The intense currents of a lightning discharge create a fleeting but very strong magnetic field. Where the lightning current path passes through rock, soil, or metal, these materials can become permanently magnetized. This effect is known as lightning-induced remnant magnetism, or LIRM. These currents follow the least resistive path, often horizontally near the surface but sometimes vertically, where faults, or bodies, or groundwater offers a less resistive path. One theory suggests that lodestones, natural magnets encountered in ancient times, were created in this manner. Lightning-induced magnetic anomalies can be mapped in the ground, and analysis of magnetized materials can confirm lightning was the source of the magnetization and provide an estimate of the peak current of the lightning discharge.
In culture.
In many cultures, lightning has been viewed as part of a deity or a deity in and of itself. These include the Greek god Zeus, the Aztec god Tlaloc, the Mayan god Ke, Slavic mythology's Perun, the Baltic Pekons Perknas, Thor in Norse mythology, Ukko in Finnish mythology, the Hindu god Indra, and the Shinto god Rajan. In the traditional religion of the African Bantu tribes, lightning is a sign of the ire of the gods. Verses in the Jewish religion and in Islam also ascribe supernatural importance to lightning. The expression lightning never strikes twice, in the same place, is similar to opportunity never knocks twice in the vein of a once-in-a-lifetime opportunity, that is, something that is generally considered improbable. Lightning occurs frequently and more so in specific areas. Since various factors alter the probability of strikes at any given location, repeat lightning strikes have a very low probability, but are not impossible. Similarly, a bolt from the blue refers to something totally unexpected. Some political parties use lightning flashes as a symbol of power, such as the People's Action Party in Singapore, the British Union of Fascists during the 1930s, and the National States' Rights Party in the United States during the 1950s. The Schutzstaffel, the paramilitary wing of the Nazi Party, used the SIG rune in their logo, which symbolizes lightning. The German word Blitzkrieg, which means lightning war, was a major offensive strategy of the German army during World War II. In French and Italian, the expression for love at first sight is coup de foudre and colpo di fulmine, respectively, which literally translated means lightning strike. Some European languages have a separate word for lightning which strikes the ground, as opposed to lightning in general. Often it is a cognate of the English word raise. The name of New Zealand's most celebrated thoroughbred horse, four-lap, derives from the shared Zhuang and Thai word for lightning. The bolt of lightning in heraldry is called a thunderbolt and is shown as a zigzag with non-pointed ends. This symbol usually represents power and speed. The lightning bolt is used to represent the instantaneous communication capabilities of electrically powered telegraphs and radios. It was a commonly used motif in Art Deco design, especially the zigzag Art Deco design of the late 1920s. The lightning bolt is a common insignia for military communications units throughout the world. A lightning bolt is also the NATO symbol for a signal asset,